Prepare to have your perspective shattered and your mind stretched beyond its limits as we delve into the mysteries of existence itself. These are the revelations that challenge the very foundation of our understanding, revealing a reality far stranger and more wondrous than we could have ever imagined. The arrow of time. It is a concept that describes the asymmetry of events in our universe, the fact that time seems to flow in a particular direction, from the past to the present and on to the future. This notion is deeply intertwined with the second law of thermodynamics and the observed behavior of physical processes. Let's delve into the details. Entropy and disorder. The second law of thermodynamics states that the total entropy or disorder of an isolated system tends to increase over time. This means that in natural processes, things tend to become more disordered and spread out as time goes on. Irreversibility, like a cup of hot coffee cooling down, show a distinct before and after. This process is irreversible once the coffee cools. It doesn't spontaneously become hot again. The increase in entropy is closely tied to the direction of time's arrow. In the early universe, conditions were much more ordered and less chaotic. As time progresses, the universe becomes more disordered, and this increase in entropy points toward the forward direction of time. We can remember the past, but not the future. We experience events sequentially, with cause preceding effect. This alignment with the direction of increasing entropy gives rise to our intuitive sense of time flowing in a particular direction. The cosmic microwave background radiation, leftover heat from the Big Bang, is more uniform than we would expect if the universe's early state was random. This is consistent with the idea that the early universe had lower entropy and has evolved toward higher entropy over time. Origin of the arrow. The question of why the universe started in a low entropy state, the Big Bang, and moves toward a high entropy state is a fundamental mystery. Some physicists suggest that the arrow of time might be linked to the initial conditions of the universe or the way the universe interacts with higher dimensions. While our everyday experiences show time as irreversible, the laws of physics themselves don't inherently distinguish between past and future. Most physical laws are time-symmetric, meaning they work the same way whether time runs forward or backward. The arrow of time raises philosophical questions about the nature of time, causality, and the origins of our universe. It's a central topic of discussion in physics and cosmology, offering insights into the fundamental nature of reality. In summary, the arrow of time is a fundamental characteristic of our universe, rooted in the increase of entropy over time. The direction of time's flow, from past to future, shapes our experiences, the behavior of physical processes, and our understanding of the unfolding cosmos. Quantum entanglement. Imagine you have two particles. Let's call them particle A and particle B. In the quantum world, these particles can be in a state where their properties, like their spins or energies, are uncertain until measured. This uncertainty is described by something called a probability wave. Now, let's say particle A and particle B are created together in such a way that their properties are entangled. This means that their probability waves are linked in a special way. When you measure one particle, let's say particle A, its probability wave collapses, determining its property. What's fascinating is that the moment you measure particle A, the probability wave for particle B collapses too, instantaneously determining its property, no matter how far apart they are from each other. This instantaneous connection, where the state of one particle influences the state of the other, is what's known as quantum entanglement. It's as if these particles are communicating with each other faster than the speed of light, which challenges our usual understanding of how information can travel. The phenomenon becomes even more puzzling when you consider that this entanglement persists even when the particles are separated by vast distances. This has been confirmed through many experiments, including ones where entangled particles were sent to opposite sides of the planet. One of the most famous thought experiments that illustrates this is called the EPR paradox, named after Einstein, Podolsky, and Rosen, who proposed it. They used quantum entanglement to show that there must be some hidden variables that determine the properties of the particles in advance, making the apparent instantaneous connection less strange. However, later studies in the violation of Bell inequalities have suggested that such hidden variables might not exist, and that entanglement is indeed a genuine and non-local phenomenon. Quantum entanglement challenges our everyday understanding of cause and effect, and it's a key part of what makes the quantum world so different from the world we're familiar with. It's a fundamental aspect of quantum mechanics and continues to be an area of intense research and fascination among physicists. Conscious observer paradox. This paradox is a perplexing idea that arises in the realm of quantum physics and raises questions about the role of consciousness in shaping reality. Let's explore this paradox step by step. Quantum measurement. In quantum physics, particles exist in a state of probability until they're measured. This means that, before being observed, a particle can be in multiple states at once, a concept known as superposition. When you measure the particle, its probability wave collapses into a specific state. Observer effect, the act of measurement or observation, seems to have a profound impact on the behavior of quantum particles. This is known as the observer effect. For instance, simply observing which slit a particle goes through in the double-slit experiment changes the outcome, from wave-like interference to particle-like behavior. Consciousness and reality. Here's where the paradox emerges. Does the act of observation by a conscious observer actually cause the particle to choose a state? Does the presence of consciousness somehow influence the outcome of a quantum experiment? The paradox, if consciousness does indeed play a role in determining reality at the quantum level, it raises complex questions. How can something as abstract as human consciousness have a direct impact on the behavior of subatomic particles? Does this imply that consciousness is somehow fundamental to the fabric of reality itself? Interpretations. Different interpretations of quantum mechanics propose various solutions to this paradox. Some argue that consciousness is intimately tied to the physical world, while others suggest that the act of measurement itself, regardless of conscious observers, is what causes the wave function to collapse. Critiques and challenges. The conscious observer paradox is met with skepticism by some physicists who emphasize the role of decoherence, the interaction of particles with their environment, as the main cause of wave function collapse, regardless of conscious observation. Philosophical implications. The paradox delves into the philosophical realm, raising questions about the nature of reality, the relationship between mind and matter, and the fundamental principles that govern the universe. It's important to note that the conscious observer paradox remains a topic of debate and speculation within the scientific and philosophical communities. While some interpretations of quantum mechanics seem to suggest a connection between consciousness and the collapse of the wave function, there is no consensus on the matter. The paradox continues to inspire discussions about the nature of the quantum world and its interaction with our understanding of consciousness and reality. The double-slit experiment. It is a cornerstone of quantum physics that reveals the mind-boggling behavior of particles at the tiniest scales. Let's dive into the details. Imagine you have a wall with two small slits in it, and behind the wall, there's a screen. Now, imagine you're shooting tiny particles, like electrons or photons, particles of light, at the wall. You might think that these particles would just go through one slit or the other and create two neat lines on the screen behind, like throwing two balls through two holes in a fence. But here's where it gets weird. When you actually perform this experiment with particles like electrons or photons, something unexpected happens. Instead of getting two neat lines on the screen, you get an interference pattern, a pattern of alternating light and dark bands, like ripples in a pond when you throw in a pebble. This interference pattern looks like what you'd get if the particles were behaving like waves, spreading out and creating patterns of overlapping waves. This is strange because particles like electrons are usually thought of as individual, discrete entities, not like waves. To make it even more puzzling, if you try to figure out which slit each particle goes through by placing detectors at the slits to see which one the particle goes through. The interference pattern disappears. Instead, you get two separate lines on the screen, as if the particles are no longer acting like waves, but more like individual balls going through the slits. This phenomenon demonstrates the wave-particle duality of quantum particles. It's like particles can be both waves and particles at the same time, until we look at them and force them to choose one behavior over the other. This behavior challenges our intuition and has profound implications for how we understand the nature of reality at the quantum level. The double-slit experiment isn't just a theoretical concept. It has been conducted with particles ranging from electrons to even larger molecules. It remains a fundamental experiment that continues to spark discussions and debates about the nature of quantum reality and the role of observation in shaping it. Eternal inflation. This is a complex concept that arises from theories in cosmology, specifically in the context of inflation theory and the multiverse hypothesis. To understand it, let's break it down step by step. Inflation theory. In the early moments of the universe, there was a period of rapid expansion known as cosmic inflation. This inflationary phase explains why the universe appears so uniform and why galaxies are spread out the way they are. It also suggests that the universe expanded much faster than the speed of light during this phase. Multiverse hypothesis. The multiverse idea suggests that our universe is just one of many universes that exist within a larger structure called the multiverse. Each universe in the multiverse could have different physical properties, laws of physics, and even dimensions. Eternal inflation. Now, imagine that during the inflationary phase, some parts of the universe stopped inflating while others continued to inflate. In regions where inflation stopped, galaxies, stars, and planets formed. These are the regions we can observe today. However, in regions where inflation continued, new bubble universes could form within the fabric of space-time. Here's where the concept of eternal inflation comes into play. The process of inflation might not have ended completely everywhere. Some regions of space could continue to inflate, giving rise to new universes within these bubbles. This process could be ongoing, leading to an infinite number of bubble universes continuously forming. It's important to note that these bubble universes might have different properties, different physical constants, particles, forces, and even dimensions, making them vastly different from our own universe. This idea raises the possibility that the physical laws we observe in our universe might just be one set of rules among many. However, eternal inflation is a theoretical concept with many complexities and challenges. It's not directly observable, and different models of inflation and the multiverse lead to different predictions and implications. As such, it remains a subject of ongoing research and debate among cosmologists and theoretical physicists as they strive to understand the nature of our universe and its place within a potentially vast and diverse multiverse. Simulation hypothesis. It is a thought-provoking idea that suggests our reality might be a computer simulation created by a more advanced civilization. Let's break down this concept step by step. Virtual reality and simulation. Imagine you're playing a video game or using a virtual reality headset. In these environments, you interact with a digital world that seems real to you, even though it's actually made up of bits of data and code. The simulation hypothesis proposes that our entire reality, including the universe and everything in it, could be a kind of computer simulation. Advanced technology. The idea is that if a highly advanced civilization were capable of creating incredibly powerful computers, they might be able to simulate a universe as complex as ours. In this simulation, everything we experience from the tiniest subatomic particles to the vast galaxies could be generated by their computational machinery. Digital physics. The simulation hypothesis is linked to the concept of digital physics, which suggests that at the most fundamental level, the universe operates like a computer program, with information and computation playing a central role in how reality functions. indistinguishable reality. From the perspective of the beings within the simulation, us, the simulated reality, would be indistinguishable from what we consider the real reality. Just like characters in a video game might think their world is genuine, we might perceive our world as completely real, even if it's generated by complex algorithms in a computer. Evidence and implications. Proponents of the simulation hypothesis point to certain phenomena in physics, such as the limits of the smallest measurable units of space and time, Planck units, as potential clues that our reality is somehow pixelated or discretized, a trait common in digital simulations. However, this remains speculative and doesn't constitute concrete evidence. Philosophical and ethical questions. The simulation hypothesis raises profound philosophical questions about the nature of consciousness, free will, and the purpose of existence. It also prompts ethical considerations about the intentions of the simulation creators, the ethical implications of running such a simulation, and our role as simulated beings. It's important to note that the simulation hypothesis is a speculative idea, and there's currently no direct evidence to support or refute it. While it sparks intriguing discussions among scientists, philosophers, and enthusiasts, it remains a concept that invites both wonder and skepticism. Whether our reality is a product of a cosmic computer or not, exploring the boundaries of what we know and contemplating the nature of existence itself is a thought-provoking journey. The Fermi Paradox. This paradox is a thought-provoking puzzle that highlights the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and the lack of observable evidence for their existence. Let's break down this paradox step by step. Vast universe and high probability. The observable universe is incredibly vast, with billions of galaxies, each containing billions of stars. Given the sheer number of stars and potential habitable planets, the probability of life emerging elsewhere in the universe seems high. Drake equation. The Drake equation is a formula used to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It takes into account factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. The silence problem. Despite the high probability of extraterrestrial civilizations, we have not yet detected any clear and unambiguous signs of their existence. This is the core issue of the Fermi Paradox. If they're out there, where are they? Why haven't we heard from or seen any advanced alien civilizations? Possible solutions. Rare Earth hypothesis. Some argue that Earth-like conditions are rare, and the emergence of life is a highly unlikely event. Great filter. This theory suggests that there might be a filter that prevents civilizations from advancing to the point of widespread space travel and communication. It could be a technological, biological, or societal obstacle that limits the development of advanced civilizations. Sustainability issues. Advanced civilizations might self-destruct due to technological or environmental factors before they become capable of interstellar communication. Zoo hypothesis. Some suggest that advanced civilizations are deliberately avoiding us, like a cosmic zoo, to let us develop without interference. Transcendence. The concept that advanced civilizations might transition to a form of existence beyond our current comprehension, making traditional communication methods obsolete. Search for extraterrestrial intelligence. ACTI efforts to detect signals from extraterrestrial civilizations have so far been unsuccessful. These efforts involve scanning radio frequencies, looking for patterns that could indicate intelligent communication. The future and limits of observation. It's possible that we simply haven't looked in the right places or used the right methods to detect extraterrestrial signals. Our current technology might have limitations in detecting such signals. Implications and reflection. The Fermi Paradox raises questions about our understanding of the universe, the nature of life, and the challenges of interstellar communication and travel. It also encourages us to reflect on our place in the cosmos and the potential answers to this enigmatic question. In summary, The Fermi Paradox highlights the tension between the statistical likelihood of extraterrestrial civilizations and the absence of empirical evidence for their existence. It continues to inspire scientific research, philosophical discussions, and imaginative speculations about the possibility of life beyond Earth. As we contemplate these ideas about existence, we find ourselves at the precipice of understanding, gazing into the abyss of the unknown. Our understanding of reality continues to evolve, unveiling new layers of complexity and mystery that beckon us to explore further, to question deeper, and to embrace the infinite wonder that is the fabric of existence. Thanks for watching. Please like and subscribe to our YouTube channel.